All right, so power in a balanced system, not surprisingly, is not really that difficult because what we've seen about, now we are dealing with AC sources, right? So we do have to deal with all of the complex power ideas that we used in chapter 11. But in a three-phase system, it's pretty straightforward to look at each of the phases as its own system, essentially, right? So the complex power is going to be the sum of the power in each of the phases. The phase doesn't really affect the power very much, right? And so because we just saw each of those phases in a balanced system is 120 degrees out of phase with the previous, the complex power for a complete three-phase system is just 3 times the power of one of the phases, right? So that's pretty nice. It makes it a little bit easier to deal with. So all of those expressions that we had before in chapter 11, just to remind you. That's not the best marker. So the complex power in the three-phase system is just 3 times the complex power of one phase. Remember that when we're doing complex power, this is going to be the voltage in the phase times the current in the phase. And we're dealing with RMS in these cases, right? So we can use the other expressions as well. Right? Everything that you were practicing in chapter 11, right? So we can multiply the phase voltage times the complex conjugate of the phase current. And of course we can make substitutions to get some expressions that are similar to ones we had before for DC circuits where we have I squared R for power or V squared over R for power. Now with complex power, it's IP squared times the impedance of one phase. But if we're looking at it for the voltages, just like again we saw in chapter 11, it's the phase voltage squared divided by the complex conjugate of the phase impedance. Okay? So again, not terribly difficult. In polar or complex form, remember this was written down as the average power plus J times the reactive power, Q, right? And so for the complex power in a three-phase system, we can also express it this way, right? And this theta here is just the theta of Z, of the impedance. So the first expression up here is for the phase voltage and phase current. This bottom expression is if we know the line voltage and line current. Okay, we can calculate it that way. So again, pretty straightforward. But the nice thing I mentioned previously that with three-phase power, one of the main reasons that it is so popular is that it allows us to get our power more economically, right, for a variety of reasons. So we can kind of choose which way we want it to go. So if we were looking at a single-phase system, right, it uses 2 wires. Right? The single-phase system, current flows in from the source to our load, back out, right, through the neutral line or whatever. This is like what we have in our house, one of these wall sockets on the ground. Even though there's a third wire, these are not 3-phase systems, right? These are all single-phase. The third pin is just a ground. So in this case, we can figure out what the power is, right? By knowing what our load is, and we can look at the power as just being the voltage on the load times the current flowing through the load, right? VL times IL. And that would be the power that's lost in our system, right? Depends again on our load. But in a balanced three-phase system, right, we're able to send some of the current down each of the wires. But each of the wires may have a different resistance, so that's why they're labeled R prime, right? And then we can use our expressions here to calculate the power loss in our load for the three-phase system. And we call this, right now, we call this P prime, right? So the P prime, or the power loss, is found from R prime, right? Which we're going to have 3 of those. And then we have the line voltage, or sorry, the power lost originally divided by the voltage of the line, okay, in the three-phase system. So the P sub L is that's a different expression we have here, sorry. So P sub L is like the single-phase power loss. So they're calculating this, saying that the current in the line, IL, initially, right, from this expression, they're using this, right, just P equals I times V, right? And so then if they use that expression for the line current, then they're able to make a substitution here to find the power lost in the three-phase system. R prime over PL squared times over VL squared. Where this becomes powerful is, well, okay, big deal, right? However, if we're willing to take the same power loss, right? In other words, I calculate this and I lose 100 watts of power through this system, right? And the main thing, of course, that I'm really worried about, it's actually not so much the power in the load, although that does decide what current flows, right? But the loss is power lost in the line itself. So that's really what we're looking at, right? So this R, which is the resistance of the wire, is the power loss. That's wasted, right? So in the three-phase system, I'm using a different resistance. Each of the wires, right? There's 3 wires now instead of 2. So again, we're assuming, we still want the same current and voltage to flow to deliver the same power to our load. But how much do we lose because of that in the wire? Well, that depends on this new resistance. And so if we're willing to subject ourselves to the same power loss, right? So the power loss here equals this power loss prime over here, then we can actually do some pretty straightforward little calculations. And they show us, okay, power loss divided by the power loss prime, right, ends up giving us 2 times the resistance over the resistance prime, right? So the power loss here, there's 2 R's, right? And over here, the loss is by 1 R prime. So then we can look at these and remember the geometric form for resistance. Where does resistance come from, right? Remember that R equals rho L over A, right? While assuming that we're made of the same material and we're trying to go the same distance, so L and rho are the same, the only thing that's different is A, right? And A is pi R squared, right? So making that substitution, instead of having this be R over R prime, this gives us it works out to be 2R prime squared over R. So the radius, now this is not resistance or resistivity, this is the radius of the wire. So the radius of the three-phase system divided by the radius of the single-phase system, right? So when we look at this and say, okay, now what about the material that actually requires? How much copper does it take to make these wires, right? So then I can figure out the volume of copper. So I know that I'm going to need to have, in the single-phase system, I'm going to have whatever this R is, right? You're going to have so for the single phase, right, we're looking at single phase over 3-phase. And this is the material. In our single-phase system, then I've got the cross-sectional area, pi R squared, times the length is the volume of metal in one wire. And there's 2 wires in the single-phase system, right? 2 pi r squared times L over, in the three-phase system, right, I have 3 wires times pi r prime squared times L. Yeah.
So you're assuming that all the r primes are the same value?
Yeah. Yeah, of course. You're figuring, they're assuming that it's the same wire, right?
The same distance.
And the same distance, because this is essentially this is a cable, right?
Okay.
So just like any of these power cords here, right? In fact, unfortunately, my power cord is starting to fray, but if you look inside the casing, right, you guys can probably just barely see, there are actually 3 wires. We've all looked inside of a cable before, right? So there are 3 wires inside. One is in this case, one is the hot wire, right, the one carrying power to my load. The other is the neutral, carrying the power back to my source. And then the other is a ground, which is just a safety, essentially. It's an extra wire to carry away if there were a short circuit or something like that. So the ground is being ignored in both of these cases, because we can have a separate ground wire on these guys as well if we needed to. So in the three-phase system, similarly, we're assuming these 3 wires are actually one big cable, right? And in this case, it's like 2 wires inside of a single cable. So the length has to be the same. And we're going from our power station or whatever to our house or building. So the length is going to be the same as well, right? We're not changing any of those dimensions. So in this case, in fact, if we want to make these powers match, we know from this previous equation right here what the relationship between r prime and r is. So we can make a substitution, right? Because we know. Did I forget the square? I think I forgot a square on this one. Right. If we're going to have the same power loss in both systems, this has to be 1, which means that the 2r prime squared over r squared is 1. Right? So they have to be equal to each other. R squared equals 2r prime squared. And so if I substitute that in here, this gives me 1.33. What does that mean? It means that in fact, the material in the single phase is 1.33 times more than the material in the three-phase system. It seems a little bit counterintuitive, right? I'm running 3 wires instead of 2 wires, and yet I'm using less material. Why is that happening?
Carrying less current in each wire?
Exactly. Less current in each wire allows me to have a slightly higher resistance wire, meaning the wires can be a little bit thinner, right? And since the thinness, right, gives me material like r squared, a little bit thinner is a big difference. So in fact, a single phase system requires 33% more material. That's a lot if you start thinking about how much copper is in a power distribution system. You know, how many feet of wire are in the United Illuminating distribution system? Honestly, I don't know. They serve about a half, roughly, of Connecticut. So I think they must have somewhere in the neighborhood of at least 1,000 miles of cable, probably, right? And copper wire that they run costs about anywhere from, depending on, well, if it's big power transmission, it's going to be more expensive, but it's going to be somewhere in the neighborhood of $1.50 to $2 a foot, right? 5,000 feet in a mile, 1,000 miles of cable, 5,000 miles of cable, whatever you want, that big number you want to pick, right? You're talking millions and millions of dollars worth of material. So if I can save 33% of that, that's a huge savings, right? And it also, even more than that, when you think about what it costs for those cables, imagine if all of the power systems in the country were trying to run single phase. They would all need 33% more copper. what would that do to the price of copper, right? There would be a huge demand for copper. We wouldn't even hardly be able to mine enough copper, right? And so the price of copper would go up and it would cost even more, right? So the economics of it are incredibly favorable to actually use three-phase power systems, right? And then on top of that, when you figure that a whole bunch of power that we use actually goes to driving motors, and the motors actually work better when they're three-phase motors. They're more efficient and they operate better, they run more smoothly, then it's kind of a win-win situation. The only thing that makes it a little bit uncomfortable, if you will, is that then you have to worry about when you go from a three-phase to a single-phase system, because in the household, we deal with everything on single phase. Right? So how do you do that? Well, in moving to a residential style, there's a section on this book.